Hey, good morning, guys. This will be a review of differentiation techniques from Calc 1. This is not meant to be watched by anyone who's taking Calc 1. This is going to be perhaps either you're at the end of Calc 1. I'm not going to be going into any amount of sufficient detail as perhaps when you would take Calc 1 originally. So this is really geared towards folks taking Calc 2 perhaps, or maybe need a refresher in Calc 3. Let's get started. So we'll be discussing these 8 canonical rules, and we'll do some practice problems with each. But starting with the power rule, the power rule is used whenever you have 3 conditions being satisfied. So you have a variable in the base, and a number in the exponent, or in the power. So, which is to say, it should look something like x to the, say, 3 over 5. There's no restriction on what that number in the power can be. It just has to be, the variable needs to be in the base, and the number, whatever the number happens to be, pi, e, 3, 5, -7, those numbers have to be in the exponent. Second, there should be no variables in the denominator or radicals over variables. So what you should not have is something like 1 over x to the third. Oops. So on something like that, you could modify it algebraically to be able to use the power rule on it, but you can't use it as it's written. As it's written, we would have to use the quotient rule, which will come up in a second. And similarly, if you have something like square root of x, you cannot use the power rule on it the way it's written. You'd have to rewrite it as x to the 1/2 before you wanted to use, or before you were able to use the power rule. And the third condition that needs to be satisfied is that you can only use it with sums, or differences rather, or if you have individual terms. So if you just have a single term by itself and it satisfies the first 2 conditions, you can use the power rule. Or if you have a sum or a difference, so if you have, say, x squared minus x cubed plus 3x to the 5th, you only have sums or differences here, so power rule is okay. On the other hand, if we said x squared times x cubed plus 3x to the 5th, in these circumstances, power rule would not work, because you don't have just a sum or a difference. You have a product in the middle as well. So hopefully you remember from Calc 1 that in this case we would actually use the product rule. On the other hand, we could always try to do some algebra ahead of time, so we could FOIL this out, or rather distribute the x squared into both of these terms, which would give us x to the 5th plus 3x to the 7th, and then we can use the power rule on it because we've created a scenario where we just have sums or differences. So that will always be the case. Keep these 3 conditions in mind. If there's a problem that does not satisfy these 3 conditions, you cannot use the power rule on it. So with specifically the power rule, in my experience, what ends up happening with students is they use it when they're not supposed to. Using it is very simple. The more nuanced part, as it were, is knowing when to use it and when you certainly can't. For instance, if you have f of x as 3x to the 4th minus 5x to the 6th plus 9 over x squared. I have a sum or difference everywhere. I do have a variable in the base and a number in the exponent everywhere. But I do not satisfy the second condition because I do have a variable in the denominator right here. So as the problem is currently written or currently set up, we cannot use the power rule on it. But if I modify it algebraically, I move the x squared term to the numerator by making the power negative. Now all those 3 conditions are satisfied. So now we can start using the power rule. So again, I still haven't talked about what the power rule itself says, but it's far more important to know when you can use it versus when you shouldn't or can't. The power rule itself is quite simple. The derivative of this function would just require you to bring down the power and then subtract 1 from it. Now, if there's a coefficient there already, you just multiply it by that coefficient. So in this particular case, the 4 would get brought down. There's a 3 there already, so 3 times 4 would give us a 12, x, and then you drop 1 from the power. So 4 minus 1 would give us a 3. And then you keep going. Minus, bring down the 6, so 5 times 6 would give us a 30. X raised to the 6 minus 1 would be a 5. And finally, here you got to be a little careful because 9 is getting multiplied by negative 2. So that's going to give us a negative 18, x. And here's another common place where mistakes happen. A negative 2 minus 1 would be a negative 3, not a negative 1. So oftentimes, if someone's not being careful, you can add a 1 instead of subtracting a 1. So just be very, very careful. If you're finding derivatives using power rule, you got to bring down the power, subtract 1 from the exponent. But you can only do that if these 3 conditions are satisfied. So this would be minus 18x to the negative 3. And that would be the answer. That would be the derivative of a function f of x using the power rule. Hopefully that makes sense. Before I move on to the product rule, this is a problem that you cannot use the power rule on. The very first condition is not satisfied or is violated because we don't have a variable in the base. The variable is in the exponent, so that's in the wrong spot. And the number should be in the power, but the number's in the base. That's in the wrong spot as well. So power rule definitely does not work here. But this is a completely different family of functions. It's called the exponential function. Those we will have to deal with very, very differently. We're going to have to do something completely different to find the derivative of exponential functions in due time. But hopefully that covers or reminds you of how to use the power rule. So I'm going to mark that complete. With regards to the product rule, so this remains semi-organized. For the product rule, oftentimes students will memorize it as f prime g plus g prime f, which is fine, and if you can solve all product rule questions that way, by all means continue to do that. My recommendation would be to perhaps think of this in terms of plain English sentences, because then if f and g get swapped, you still don't make a mistake. But if you only memorize the formula with f's and g's or u's and v's, there's a potential for a mistake. The potential isn't as high with the product rule because there's a sum in the middle, but with a quotient rule where you get a subtraction or a difference in the middle, that's where it becomes very, very likely or very easy to make a silly mistake. So let's go over that in more detail when we get to the quotient rule. But the way I discuss this in my own Calc 1 class is the derivative of the first. So in this case, this is not f of x prime or f prime of x. This f just means first. Times the second. So s is not s of x. It's not another function. It just means the second function that we see. Plus the derivative of the second times the first. So you're basically just swapping the locations of the prime and adding the two things. Another way of writing this would be f times, or the first times the derivative of the second. Both are perfectly okay because of something nice called the commutative property of multiplication. It's a fancy way of saying that if we multiply 2 and 3, we get 6. But what happens if we change the location of the numbers? So 3 times 2, well, that also gives us 6. So that's just to say that if we take a second function and we differentiate it and then we multiply it by the first function, nothing will change if we put the first function first and then the derivative of the second function after it. It's still going to give us the exact same answer. So bottom line is derivative of the first times the second plus the derivative of the second times the first. Or you can continue to review it as f prime g plus g prime f. Both approaches will give you the answer, but with the quotient rule, this approach of first, second, top, bottom actually comes in a little bit more handy. So let's do a practice question here. Let's say we know that g of x is 3x squared plus 4x times, let's throw in a trig function just for review. So in this case, I'm considering this to be my first function and this to be my second function. Hopefully you remember the derivative of sine x is cosine x. If not, we'll review it when we get to trig functions. But for now, I'm going to assume that you know it. G prime of x is really quite simple if you follow the recipe. It says the derivative of the first. So the derivative of the first function that I see, 3x squared plus 4x, is going to require us to use the power rule. And it's a good time to review the three conditions. Do we have a variable in the base with a number in the power? Well, for this first term we do. A variable in the base and a number in the power. Well, if we don't have an exponent explicitly written, we assume it to be 1. So first condition is satisfied. Do we have any variables in the denominator or inside radicals? No, so we're clear on that. And do we have only sums or differences or individual terms, meaning just a single term being differentiated? Absolutely. So I can definitely use the power rule on this. So the derivative of the first would be 6x plus 4 times the second, sine x, plus, so far I've dealt with the derivative of the first times the second. I've put a plus sign. Now I have to find the derivative of the second function. So the derivative of the second would be cosine x times the first. So I don't have to touch that function. I just copy it down as I see it. Now, if you're taking Calc 1, then the requirements are different. You probably have to simplify this depending on which section you're in. So if you're optimizing something or using this derivative to find slopes of tangent lines or curve sketch, you may need to simplify that derivative. For now, the purpose of this video, so as to say, is just to remind you of the rules themselves. So I'm not going to go into algebraic simplification. It's just to remind you of the derivative rules themselves. So hopefully that makes sense with the product rule. Derivative of the first times the second plus the derivative of the second times the first. It's the exact same thing as f prime g plus g prime f, but memorizing it in words, now we'll see in quotient rule gives us a little bit of an easier time. Quotient rule hopefully is as obvious as the product rule application is. The quotient rule is used whenever you have a top function being divided by a bottom function, and then you have to find the derivative of the whole thing. So in this case, we don't have a first or a second. We don't have something going from left to right. We have something from the top and on the bottom. So in order to find the derivative of a quotient of two functions, the one phrase that I always tell my students to remember is that the bottom comes first. If you remember that, the rest of the rule just kind of perfectly falls into place. You don't have to do anything else with it. So we'll start with writing the bottom times the derivative of the top. So we alternate the primes. If we're not differentiating one function, we differentiate the other one in the formula. So if you start with the bottom, the top has to come next. With the quotient rule, we have a subtraction in the middle. And now in this scenario, I've already differentiated the top and not the bottom. So now I'm going to swap the location of the prime. I'm going to differentiate the other function. Top times the derivative of the bottom. All over bottom squared. So let's see this in action. I'm going to cheat a little bit and preview something we're about to do in a bit with trig functions. But this is actually a very good time to remind you of trig functions and the quotient rule simultaneously. So in the event, in the unlikely event, hopefully, that you forget what the derivative of tangent x is, you should definitely be able to just use quotient rule to figure it out on the fly. Personally speaking, I know the derivatives of sine, cosine, and tangent, and the other three, if I'm being completely honest, I just figure them out as and when I need them. I don't necessarily have them memorized perfectly. If you're taking Calc 1 and Calc 2, my recommendation would be that you do commit them to memory, because there's value in doing that, because you'll be doing things under timed conditions. When I'm working on problems that require me to find derivatives, it's rarely the case that I have to finish it within, say, 3 minutes or 7 minutes or whatever the case might be. I usually have a week to solve a problem. So if I need to go, scratch off to the side and find the derivative of cotangent x here, I'm not in any trouble. But if you're taking calculus currently, it would probably be to your benefit to do that, to just have them committed to memory or memorize them. So if you forgot that the derivative of tangent x is secant squared x, first thing you can do is rewrite it as sine x over cosine x. That's a relationship that I'm hoping you remember from trig. That tangent x is the same as sine x over cosine x. So in order to find the derivative of h of x, which would be to say find the derivative of tangent x, we're really just finding the derivative of sine x over cosine x. Now, let's use this rule that we just came up with. The bottom comes first. So whatever the denominator is, whatever the bottom function is, we're going to write that here. So I've dealt with that. Times the derivative of the top. Well, the derivative of sine x is cosine x. So I'm going to put that here. That goes away. Minus, so I've dealt with the minus. The top by itself, so I'm not going to touch the sine x. I'm just going to copy it down. Times the derivative of the bottom. Times the derivative of cosine x would be negative sine x. All over bottom squared, so cosine squared x. Now at this stage, we can recognize that cosine x times cosine x is simply cosine squared x. That's not too bad. And then a negative sine x times negative sine x will give us a positive sine squared x. All over cosine squared x. Hopefully you remember the Pythagorean identity. Sine squared x plus cosine squared x is 1. Well, by commutative property of addition, cosine squared x plus sine squared x would be 1 as well. And if you don't see that, think about 2 plus 3 being 5, and what happens if you swap the location of the numbers. 3 plus 2 equals 5 as well. So either way, you get the same answer. So what we can do is rewrite this as 1 over cosine squared x. Hopefully you remember also from trig that 1 over cosine x is simply secant x. So if I have 1 over cosine squared x, that's just going to be secant squared x. So now comes the value proposition. You might say, well, this takes so much time and so much effort. Why wouldn't we just memorize that the derivative of tangent is secant squared? And that's exactly my argument, that you should memorize it. However, as you get faster, as you practice it more and more, I've probably written this derivation of the derivative of tangent x probably at least 20 to 30 times. So when I write it down, I can very quickly kind of get to here. That's going to take you time. If you practice it, you're going to be able to do it reasonably quickly. But until such time, you're better off just memorizing it, having it in your back pocket for whenever you need it. But that's an example of finding derivatives using the quotient rule. I'm not going to do this. I'm leaving this as an exercise to whoever's watching this video. Make sure that you're able to find the derivatives of secant x, cosecant x, and cotangent x using the quotient rule. I think that would be excellent practice. And all that you're really required to do in order to find, say, the derivative of secant x would be rewrite secant as 1 over cosine x, and then find the derivative of that using quotient rule. Do the same with cosecant x, rewrite it as 1 over sine x, find the derivative using quotient rule. For cotangent x, write it as cosine x over sine x, and then find the derivative using quotient rule. So these I'm leaving as an exercise to the reader or to the viewer. I would very strongly urge you to do it, in part to review it, but also in part to relearn it in case you forgot it. So that is what I had planned for the quotient rule. Let's see what's next. Ooh, chain rule. All right. Chain rule is probably the most abused rule in all of calculus. Students always like to say that they use it, but in my experience, it's used or misused very, very frequently. So I'm going to write it in plain English first. It's the derivative of the outside keeping the inside the same times, and I really have to write this much larger. The derivative of the inside. Now, the reason I'm talking about inside and outside is because chain rule is always used whenever we have a composition of functions, when we have a function placed inside of another function. As a reminder, say f of x is e to the x, and g of x is cosine of pi x plus e. Let's not go that far. Let's just say pi x plus pi over 2. Now, if I were to ask you what is f of g of x, you would take the function g of x and plug it into wherever you see an x in the original function f. So that answer would be this semi-ugly looking thing, e to the cosine of pi x plus pi over 2. But that is what a composition is. When you take a function, you plug it into another, or you evaluate a function at another function, you're doing what's called a composition of functions. Whenever we do that, we have to use the chain rule in order to find the derivative. Now, there's two scenarios where this happens. With trig, exponential, inverse trig, so I'm including inverse trig functions as part of trigonometric functions. They're still in that same family. So with trig functions, exponentials, and logs, you should always be very careful to make sure you use the chain rule correctly. For all other types of functions, you can also think of the two P's of chain rule, parentheses and power. So, which is to say that if a function looks like 3x squared plus cosine x minus, I don't know, 5x, let's say, to the 10th power, here we have the two hallmarks of chain rule. We have a set of parentheses and we have a power. So sometimes it really is that obvious. If you have a set of parentheses and a power, your brain should be thinking chain rule. With exponential functions like these, it becomes less obvious because the x that was in e to the x got replaced with this function. So you don't have the traditional parentheses with a power. You don't have this neat little encapsulation that occurs. We'll get to exponential functions next, but I just wanted to kind of tease that idea here. So let's apply the rule. The derivative of the outside. So here's a trick that you can use. Imagine that you could place your thumb, maybe you have a really wide thumb, and you place it directly on top of 3x squared plus cosine x minus 5x. Or, you know, in your mind, imagine that that's just x. The reason why we're doing this is, if we were to break h of x down into the component functions, the functions that would have been composed to give us this, f of x would be x to the 10th, and g of x could be 3x squared plus cosine x minus 5x. So if I were to take g of x, which is this function, and plug it in for an x here, wouldn't we get exactly that, what we have on the left-hand side? So the outside function is x to the 10. Chain rule says find the derivative of the outside keeping the inside the same. In practice, this just boils down to bringing down the power, keeping the inside the same, so 3x squared plus cosine x minus 5x. But a common mistake that happens at this stage is students just move on to the derivative of the inside. But this is not the derivative of the outside completed. The derivative of the outside requires us to bring down the power, but also subtract 1 from it. So 10 minus 1 would give us a 9, times, so either students will forget this or they'll forget this portion. Please don't. Try to make sure that you remember to write all pieces of the chain rule correctly. Times the derivative of the inside. Now the derivative of 3x squared we can find using the power rule, so that's going to be just 6x. The derivative of cosine x, well, that's easy, negative sine x, minus the derivative of negative 5x, or sorry, minus the derivative of 5x would just be 5. And that is the answer. Now, again, if you're taking Calc 1 and you didn't listen to my advice at the warning or the warning at the beginning of the lecture, this is not as simplified as it could be. There are other algebraic manipulations we can do to clean this up. But for now, that is the derivative of the original h of x function I gave right above it. Just for the sake of practice, I wanted to throw in a reasonably complicated trig function as well. So if you have sine of, say, 3x, okay, I lied. That's definitely not reasonably complicated. But this is something that we use very, very frequently for, say, integration by parts, or trig substitution, or trig integration. You're going to run into sine of a constant times x quite frequently. So finding the derivative of this helps us when we have to find the integral later on. The derivative of the outside. So the outside function here is sine x. And the inside function, what could we have replaced this x with in order to get the 3x? Well, 3x. So the derivative of the outside function, sine x, would be cosine of x, but we have to keep the inside the same, times the derivative of the inside. The derivative of 3x is simply 3. So that's our answer. The derivative of sine 3x is cosine 3x times 3. Let's do one more. Chain rule tends to be challenging. Let's say we have x to the third plus 4 sine of 5x minus 6, and let's say all of this is inside a 7th root. Pretty ugly looking function, but we can definitely handle it. This doesn't look like the traditional parentheses with the power, but it actually is, if you remember from some algebra course, that I can rewrite, or we can rewrite this radical as x cubed plus 4 sine of 5x minus 6 raised to the 1/7. Anytime you have a radical, the index goes in the denominator of the exponent. So a 7th root is the same as 1/7 power. Now we do have the hallmarks of chain rule. We do have a parentheses and a power. So I can apply the chain rule. The chain rule would state, bring down the power, subtract 1, or the derivative of the outside, keeping the inside the same. So the derivative of the outside while keeping the inside the same would be this. You want to be careful here. 1/7 minus 1 is negative 6/7. If you're not comfortable with it, use a machine to help you out, or just do it off to the side. Convince yourself that you're not making a silly mistake in writing down the wrong power and potentially losing a whole bunch of points. Times the derivative of the inside. Now here I'm going to go slow, and I hope that you do as well. The derivative of x cubed, well, that's easy. Power rule, bring down the power, subtract 1, life is good. 3x squared. Now we move to this next term, and I'm really going to slow down here. 4 sine of 5x. Didn't we do something very simple, or similar rather, right here? Instead of 5x, we had a 3x. So So these are called nested chain rule problems, where there's a chain rule inside of a chain rule because there's a composition inside another composition. So you want to be very, very careful that you're keeping track of what the outside function is, what the inside function is, and so on and so forth. So when we find the derivative of 4 sine of 5x, we have to use chain rule again. So it's almost beneficial to forget everything else you have on your paper and just find the derivative of that and write it down. So the derivative of this function by itself using chain rule would be, the 4 would come along for the ride. It's a constant multiple. The derivative of the outside would be cosine, keeping the inside the same, 5x, times the derivative of the inside, which is 5. If you're not certain of it, look at exactly that. Minus, well, the derivative of 6 would just be 0, so I don't have to do anything with that. As far as the derivative goes, that is our answer. Now, again, as I said before, you can clean this up. You can, multiply coefficients. You can distribute the 1/7. All that stuff can happen, but that's always downstream to the derivative. That in front of you is the derivative. Next, we have, exponential and log rules. These are my favorites. Very simple as long as you remember some basic formulas. I think it's number 5. Yep. Now, the exponential rule is used anytime you have a number in the base and a function or a variable. It doesn't have to be a full-blown function, but it could be a function or a variable in the power. That's how you identify when you have to use the exponential rule. So really quite simple. If you memorize the rule, no problem. So if you have a number in the base, and the number here is represented by the letter a number raised to some function, if when differentiated, will always give us the ln of the base times the exponential function itself times the derivative of the exponent, so f prime of x. Now, this is the most general form of the exponential rule that there is. This includes the chain rule application. So oftentimes, some students are taught that, the exponential rule is that the derivative of e to the x is e to the x, and then you use chain rule to solve other problems. In my experience, just teaching everyone the most general form from the very beginning makes it a lot easier to handle. So let's run through some examples and see how this rule actually shakes out. Let's say that we were to find the derivative of e to the x using this general exponential rule. The first thing we have to do is identify the ln of the base. The base here is e, so my first piece is going to be ln of e, times the exponential function itself. So whatever we had in the problem, we just copy it again. Oops. E to the x, that's my exponential function, times the derivative of the exponent. The derivative of x is just 1. Now, if we clean this up, hopefully you recognize that ln of e is just 1. E to the x is, well, e to the x. And then times the 1, I'm just going to keep it as it is. Now, hopefully you can see that we're almost home. 1 times any quantity is always itself. So if we multiply 1 by e to the x, we're going to get e to the x. And if we multiply it by 1 again, we're going to still get e to the x. So this will simply be e to the x, which hopefully reminds you of what you may have seen in Calc 1. The derivative of e to the x is e to the x. The usefulness or the use case of this formula is not for something super simple like e to the x, which is easy enough to remember. You just memorize that the derivative of e to the x is e to the x. The true benefit comes in when we have something ugly like this. Let's do that. So we have 3 raised to the 3x to the 4th minus sine x plus 7x. In this case, you'd have to do some pretty severe contortions in order to get to the answer if you were doing it using some other methodology. But if you memorize this basic general exponential rule, this is actually a very simple problem. We always start with the ln of the base. The base in this case is 3, so the derivative will start with ln of 3 times, now we just copy down the exponential function itself. So 3 raised to the 3x to the 4th minus sine x plus 7x. We're not touching anything, we're just copying the original question as it is. And the last piece is the derivative of the exponent. So the derivative of 3x to the 4th, well, that's easy. 12x to the 3rd using power rule. The derivative of negative sine x is negative cosine x, so that part's easy as well. And the derivative of 7x is 7. Now that looks long and obnoxious, but if you know the formula, it's really quite simple. You just kind of follow the recipe, go downstream with the question itself. Just for the sake of variety, let's do one more. Let's say we have to find pi. Why not use pi? Pi raised to the cube root of x. So that would probably give some of us some shivers, but it's really a very simple problem. It requires you to remember that pi is a constant and cube root of x is a function of x. So it's really just an exponential function that looks very angry, but it isn't. It's really quite simple. In order to find the derivative of the cube root of x, remember that we had to rewrite it as x to the 1/3 first. So what I'm going to do is rewrite this as the derivative of pi raised to the x to the 1/3. Reason why I'm going to do this, well, you're going to see why shortly. So let's get started with the formula. We start with ln of the base, so it will be ln of pi times the exponential function itself, so pi raised to the x raised to the 1/3, times the derivative of the exponent. Well, what's the derivative of x to the 1/3? It's just 1/3 x to the negative 2/3. Power rule. Bring down the power, subtract 1. 1/3 minus 1 is negative 2/3. And that's your answer. No fuss, no mess. Quite simple as long as you know this formula. Now, that formula will get you through any exponential function. It doesn't matter if it's chain rule or not. If you apply it, you're going to get the answer all the way through. For the logarithmic rule, I have a similar approach. I think we're at technique number 6. There's two things to remember here. One is the change of base formula. And the other is the general log rule. So I'm going to start with reminding you of what the change of base formula is. Then we'll talk about the general log rule. So actually, let's talk about the general log rule first, because then the change of base formula, the necessity for it becomes a little clearer. So here's the rule. If we have to find the derivative of ln of some function, notice that this is the natural log, so this is base e. If we have to find the derivative of natural log, not just of x, but it could be x squared plus 3e to the 5x plus 7, or x squared minus sine x plus 5. Any function of x, the derivative will always be f prime of x over f of x. Which is to say, find the derivative of the argument. Argument is what you're taking the log of. Find the derivative, stick it on top, divided by the argument itself. So the derivative rule does not include the log in it. There's no log of f prime over f. It's just f prime of x over f of x, where f of x is the argument of the log function on the left-hand side. So let's see this in action or in practice. Let's say we have to find the derivative of, I think one of the problems I made up was something like this. Let's do that. Plus 7x, let's say. So the derivative of, maybe I should move this to the next page because of the fraction. Oops, I guess I can't. I'll move it up one. So if we have the log of a function and we have to differentiate it, I would write the derivative of the argument up top. So the derivative of x squared minus e to the 3x plus 7x needs to go on top. So derivative of x squared is 2x using power rule, minus, now this is an exponential function, so let's practice the previous rule that we just acquired. ln of the base, so that would be ln of e. You might be saying, well, if I know that ln of e is 1, why do I keep writing it? It's more for practice. The more you write it, the more you'll recognize that it's 1, and the more you'll be able to just not include it. But for now, if you're learning it for the first time, I'd strongly urge you to include it, and then drop it off as you build more comfort and facility with the approach. So coming back, ln of the base times the exponential function itself times the derivative of the exponent. The derivative of 3x is 3. Plus the derivative of 7x, which is 7, all over the argument itself. So x squared minus e to the 3x plus 7x. And that's it. That's how you find the derivative of a log of some function of x. Now, this kind of goes out the window. This rule, you'll see, is very specific in the base that's permitted. You're only allowed to do this with a base of e. You can only do this with natural logs. You might say, well, what happens if I have to find the derivative of, say, log of x squared plus 3x minus 5 with a base of, oh, I don't know, 7? In this case, we actually bring back this change of base formula from algebra land. And the change of base formula simply stated that if you have a log of a with some base b, and you want to change it, you don't want to use base b, you want to use something else in particular, let's say c, then what you can do is rewrite this problem as log of a base c over log of b base c. So the base here becomes the new argument in the denominator. The argument here remains as the argument for the numerator, but you're allowed to choose a new base of c. Now in this case, think about it. If the only rule we have is for base e, would it not make sense to just change our base to base e, and then we can use the ln of f of x rule that we have? Hopefully that makes sense, so let's do that. I could rewrite this problem as the following. ln, or if maybe you want to see it in complete granular detail, we're going to change the base from 7 to e and rewrite the argument on top. And in the denominator, I'm going to write log with the same new base, and the argument is the old base. So remember that the b went and became the argument in the denominator. Now, hopefully you also remember that log base e is never written as log base e. We just write it as ln. So this is really just finding the derivative of ln of x squared plus 3x minus 5 over ln of 7. So this problem can be rewritten as such. And now you already have a rule for finding the derivative of ln of x squared plus 3x minus 5. Why do we not have to use the quotient rule? Some of you might be asking. Well, ln of 7 is a constant. You can plug it into your machine, plug it into a calculator, and it'll give you some number, 1 point something, or maybe 2 point something, but something small, something definitely smaller than 3. Constant coefficients don't affect derivatives. So really, we could just pull the whole constant out and just find the derivative of what's in the numerator. You could have also left it inside. I'm just trying to really drive home the point that because this is a constant, I can pull it out of the derivative, so I'm only left with finding the derivative of that and nothing else. And the derivative of ln of a function, hopefully you remember from the previous discussion, is the derivative of the argument. So the derivative of x squared would be 2x. The derivative of 3x would be 3, Derivative of 5 would just be 0, so that's gone, over the argument itself. So x squared plus 3x minus 5. And that's our answer. So with the change of base formula and the log rule with base e, you can find the derivative of any logarithmic function. And it may require changing the base so that you use base e, but again, not too bad of a modification. Next, I know we already talked about trig in some detail, so I'm not going to go over that again. But just as a reminder, the derivative of sine x is cosine x, the derivative of cosine x is negative sine x, the derivative of tangent x is secant squared x, we proved that earlier, and the derivatives of secant, cosecant, and cotangent were assigned as problems for the viewer. So please make sure that at some point of time, maybe after the video or at some point of time this weekend, sit down, make sure that you actually use the quotient rule to find derivatives of those functions. The last and perhaps the most neglected topic in Calc 1 is derivatives of inverse trig functions. Now, these tend to be, in my book, in the same category as regular trig functions, in that I don't know them by heart, but I can figure them out pretty quickly. So I'm going to go over the solution sketch or the proof of, or the derivation rather, of the derivative of, say, well, I don't know, arctangent x. That's a clean-looking function. We'll come up with the differentiation technique for it, and then the ask for the viewer or the ask for the reader would be, can you do the exact same thing with the other 5 inverse trig functions? If you can do that, you'll find it much easier to memorize it, as opposed to just straight up memorizing it cold. So prove that the derivative of, say, arctan x is equal to 1 over 1 plus x squared. So that's the formula for the derivative of arctangent x, and in this case, I'm going to prove it. The exact same techniques are used to prove or to find the derivatives of the other inverse functions as well, and I would very strongly urge you to do that. We need this very extensively in integration by parts. So if you know how to find the derivatives, you'll be able to find the integral using parts. If not, then the whole thing kind of goes down the wash. So, all right, let's start with a basic idea from Trigland. Would we agree that tangent of arctangent of x would be x? Hopefully you remember that tangent and arctangent are inverse functions of each other. So if we were to find the tangent of the arctangent of something, we would just end up with what we started with. So this is hopefully a patently true statement. Now we can extend this for, say, when we're finding the derivative of arcsine, we would start with sine of arcsine of x equaling x. And then we could do the same thing with cosine. So all these problems start the exact same way. You start with a statement that you know to be true based on the idea of inverse functions. So if you take the tangent of arctangent of x, you're going to be left with what you started with, just x. So now we take the derivative of both sides with respect to x. And when we do, the derivative of tangent of arctangent of x is going to require us to use the chain rule because we have a composition. Normally, we would just have tangent x as the outside function, but that x got replaced with arctan x. So when we use the chain rule, remember, it's the derivative of the outside while keeping the inside the same. So the derivative of tangent is secant squared. We saw that derivation earlier. Keeping the inside the same. So secant squared of arctan x times the derivative of the inside. So the derivative of the inside, I don't know it, and in fact, that's exactly what we're trying to find. So I'm going to leave it exactly as that. I don't know what the derivative of arctan x is, so I'm going to leave that as the chunk. The derivative of the outside, keeping the inside the same, times the derivative of the inside. But since we don't know what the derivative of the inside is, it's perfectly reasonable to just leave it as that. Equals the derivative of x with respect to x, well, that's just 1. Now remember, we are trying to prove that the derivative of arctangent x is this statement. Would it be reasonable then to say that, hey, if I can isolate this expression and figure out what it's going to be, or what it is, I should be good. That's exactly what I'm looking for. So if I get it by itself, I should be home. What we can do then is divide this expression over to the other side. So that will yield us with the derivative of arctan x equals 1 over secant squared of arctan x. Now, this doesn't give us anything. This is just still depending on arctan x. How can we define the derivative of arctan x if it includes arctan x in the answer? That is not terribly satisfactory to us. So we want to get this to be only in terms of x and nothing else. No other functions of x, just no sine x, no tangent x, just x by itself. We do this by going back to the very beginning and recognizing one little nuance. What is the only thing you can take the tangent of? So think back to your trig days. When you said tangent of something, what was that something always? It was always an angle. So if you think back to maybe a right triangle or a unit circle, whatever explanation you had or you were given for the existence of trigonometric functions, this angle, let's call it theta, we could always find the tangent of that particular angle. In this case, specifically, we're finding the tangent of arctan x. Wouldn't that require arctan x to be an angle then? So if you can follow along with that, you got to understand that arctangent of x is some angle. It might be 30 degrees, 45 degrees, pi over 6, pi over 3, pi over 2. I don't know what it is, but it is some angle. Well, if it is an angle, I should be able to do a whole bunch of trig with it. So if this is arctangent of x, tangent of some angle, isn't it always opposite over hypotenuse? Oh, I'm sorry, opposite over adjacent. So if we know that tangent of some angle is equal to x, doesn't that mean that the opposite has to be x and the adjacent side has to be 1 then? Well, if that's the case, tangent of arctangent of x, if that's equal to 1, the opposite side of this angle is going to be x. The adjacent side is going to be 1. Now we're looking at a right angle triangle where two sides are given. It should be begging for us to find the third side. And hopefully you remember the Pythagorean theorem. We should be able to come up with the length of the third side using the Pythagorean theorem. So let's call this the question mark side. We know that 1 squared plus x squared will give us question mark squared. Well, how would we find the question mark? We would take the square root of both sides. So 1 squared is simply 1, plus x squared is just x squared, and that gives us question mark squared. And as I said before, in order to get the question mark by itself, we can take the square root of both sides. So that tells me that the length of this missing side here is 1 plus x squared raised to the 1/2, or square root of 1 plus x squared. Now that this side show has kind of finished, we can go back, and we're a couple of steps away from finishing the problem. If arctangent x is an angle, we should be able to come up with secant of that angle as well. We know that secant of some angle is always hypotenuse over adjacent. So if I wanted to find out what the secant of arctangent of x was, I would need to do, just as a side note, as a reminder, secant of some angle is always hypotenuse over adjacent. So looking at our triangle, the hypotenuse is this quantity, square root of 1 plus x squared, and the adjacent side is simply 1. So this would give me secant of arctangent of x will be the hypotenuse, 1 plus x squared inside of a radical, over the adjacent side, which is 1. But remember, I'm not looking for just secant of arctangent of x. I have to square that answer because I'm looking for secant squared of arctangent of x. So this answer needs to get squared. What happens when we square a radical? Well, we just get the radicand. So this would be 1 plus 1 over x squared over 1 squared, which is just 1. Anything divided by 1 is itself. So the answer is 1 plus 1 over x squared. And if you trace these equal signs back to where they came from, this was equal to this, which was equal to that, which came from here, and that came from there. So this indicates that the derivative of arctangent of x is equal to this, but this was not exactly in the form that we wanted. So we made a right triangle using arctangent x as the angle, came up with a third missing side of the triangle, and then we're able to eventually rewrite secant of arctangent of x using the sides of the triangle, but because we had a square, we had to square that answer, and that cleaned up to 1 over 1 plus x squared. All of this, it may seem overwhelming, but this is something that we will do very, very frequently, pretty much in every single problem in trig substitution, which is 2 sections away. So the upcoming day we're going to be talking about, in Calc 2, we're going to be talking about trig integrals, but immediately after that class meeting, we're heading into trig substitution. Understanding this proof and being able to do it yourself for the other 5 inverse trig functions is going to make your life a lot easier when we get to trig substitution. So please, 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 for the 5 remaining inverse trig functions and for the 3 trig functions, secant, cosecant, and cotangent, find the derivatives. Find the derivatives of those 3 trig functions using quotient rule, and for these 5, follow this exact blueprint. You're more than welcome to share the solutions in Slack. I'm happy to provide feedback. But I think that's it. Yeah, so we went over product rule, quotient rule, chain rule, exponential, log, derivatives of trig functions, with 3 of them left as exercises. I sketched out the derivative of arctangent of x as 1 over 1 plus x squared, and I'm leaving the other 5 as exercises. That's it. Hopefully you found that useful, and I guess I'll see you guys in class. Take care.